Hello students and welcome to a new lecture. In this lecture here we will be addressing the gas laws. The first law we will start with is Boyle's law. Boyle's law studies the relationship between the pressure and the volume of a gas as long as we keep the amount of gas, in another word number of moles, constant and the temperature constant as well. We will find that there is an inverse relationship between the volume of the gas and its pressure. When you increase the volume, think about it, then the particles will hit less, right? They will collide less, and therefore it will drop the pressure. And when you make the volume of the container smaller, then the chances of collision between the particles and the walls of the container will increase, and as we have seen before, more collision, more pressure, so the pressure will increase. You can see right now here in this table that when you increase when you are actually decreasing the volume, so the volume keeps going down, what happens to the pressure? The pressure keeps increasing. And if I multiply the pressure by the volume, that amount stays constant. Why? One of them increases, the other one decreases. So when you multiply them, that amount will stay constant. So, if I am saying, to understand where is this law coming from mathematically, I am saying there is an inverse relationship between the pressure and the volume. Therefore, if I want to get rid of the relationship sign here mathematically, I should have equal and then put a constant over volume. So what does that mean now? If we arrange this equation to put constant at one side, that if I multiply pressure by volume, that is equal constant. Therefore, since this is a constant, I can now say that P1 V1 equals P2 V2. So this is the first initial pressure and volume. If I change one parameter here, then the other one will change as well, and therefore that will be P1 V1 equals P2 V2. Like here, like if you multiply these two, you will get this constant, and if you multiply these two, you will get this constant. This is like the before, this is the after. Now, as you can see, what happens here, when the pressure goes down, the volume goes up, right? That is an inverse relationship between the pressure and the volume. And that means there is a linear relationship between the pressure and 1 over volume. And that is Boyle's law. So the way we express Boyle's law again, P1 V1 equals P2 V2 as long as the temperature is constant and the amount of gas is constant. This is here an application of, like scuba diving is an application of Boyle's law. Every 10 meter or 33 feet of depth leads to an additional 1 atmosphere. So when the divers go down, there is the atmospheric pressure, and then there is the pressure that comes from the water, and therefore they will be under, for example, 3 atmospheric pressure if they go deep 20 meters, let's say. Okay? So the first thing about scuba diving lesson is when you descend, when you ascend back, you have to do it really slowly. Why? It's because, simply put, if you are under high pressure, what happens to the lung volume should go down because the pressure is very high. So if you go up very fast and the pressure decreases very fast, then you don't give the lung the opportunity to expand properly at its own time. So that might actually cause the lung to have an explosion, and that definitely will cause death. So this is why the first lesson in scuba diving is normally please ascend slowly. You can't just be at the bottom and then come up very fast, because that will be a significant change in pressure and that the lung is experiencing. Here is a question that we can solve together. A sample of chlorine occupies a volume of 946 milliliter and a pressure of 726 millimeter mercury. What is the pressure of the gas in millimeter mercury if the volume is reduced at constant temperature to 154 milliliter? So the first thing I'm going to teach you about the gas questions is to first identify this is what I call a before and after question. And a before and after questions, it means they took one parameter of the gas and changed it and want to see what happens to something else. And the question here is yes, they are changing the volume and they want to know what happens to the pressure. If that's the case, you should start by doing this. I normally put my before and after conditions. So what I'm going to do here, what do I have before? I have an initial volume, which is V1 equals 946 milliliter. I also have an initial pressure, which is P1 equals 726 millimeter mercury. What do I have after is V2, which equals 154 milliliter. And what we are trying to find out is P2. Okay, so this is here. It also not only it will make me not to mix things up, but it will also help me to figure out what law I'm going to use, because as you will see in this lecture, we will be using multiple laws. So it is P1V1 equals P2 V2, and I am solving for P2. So P2 equals P1 V1 over V2. Now you just put the numbers, and it's really nice that I already have them down. So I have 726 millimeter mercury, please include the units, times V1 is 946 milliliter, divided by V2 in this case is 154 milliliter. Make sure that the units are canceling out, so milliliter is canceled with milliliter. And what does that mean? That your answer will come out in millimeter mercury, which is fine because this is what the question is asking. Now, if you perform those numbers and you log them in your calculator here, so we have 726 millimeter mercury times 946, and then we divide this by 154. The answer will be 4,460, because I need 3 sig fig, millimeter mercury. So there is a logical check here. What I did, I significantly lowered the volume. Should I expect the pressure to increase? Absolutely. And did the pressure increase? The answer is yes. Okay. Now, next law we will talk about is Charles' law. Charles did study the relationship between volume and temperature. And the temperature here, please pay attention. The temperature that we are talking about is the temperature in Kelvin. So this is a relationship between volume of the gas and its temperature in Kelvin. That relationship is not going to be working if the temperature was expressed in any other unit than Kelvin. We have the amount constant, and we have also constant pressure for this gas law to apply. Hot balloon is a very significant here. When we heat the air by igniting the flame, the air gets hot and it expands and it fills like the whole balloon. Another cool one here, if you have a balloon and this balloon had little air in it, if you dip it in ice cold water, the gas inside will get colder and therefore the volume will shrink. And if you dip it in boiling water, the gas inside will get hotter and therefore it will expand in volume. So this is a direct relationship, meaning when I increase the temperature, the volume does increase as well. This is here a diagram to show you that when I increase the volume, which is the y-axis, temperature does increase as well, and that applies to multiple different pressures. The way we express Charles' law comes from the following. So we are saying that temperature or volume is directly related to temperature. Okay, now it means volume equal constant times temperature. If I want to put constant at one side of the equation, that is V over T equals constant, and this is where this law comes from. V1 over T1 equals V2 over T2. Remember that temperature has to be expressed in Kelvin. So in this class, just add 273 to degrees Celsius, and that will take you to Kelvin. Let's look at this equation or this question together. A sample of carbon monoxide gas occupies 3.2 liter at 125 degrees Celsius. At what temperature in degrees Celsius will this gas occupy a volume of 1.54 liter if the pressure remains constant? This is here, again, two conditions question. So I do this. I have condition 1 and I have condition 2, or before and after. What I have here is V1 equals 3.20 liter. I also have T1 equal 125 degrees Celsius. I immediately add 273 because I need this in Kelvin. And that's the temperature that I need. The after, I do have V2, and that equals to 1.54 liter. And I'm going to have to find T2, which is what they need. So now I just apply V1 over T1 equals V2 over T2. I am solving for T2, so if you do cross multiplication, that's T2V1 equals T1V2, and if you solve for T2, that is T1V2 over V1. So you see why it's really nice to label them from the get-go. Now, when you put everything you need, you have T1, which is 398 Kelvin, times V2, which is 1.54 liter, divided by V1, 3.20 liter. And now you are going to put all these numbers, and if I multiply 398 times 1.54 and I divide by 3.2, that is going to give me 192 Kelvin. They wanted in degrees Celsius, so I'm going to subtract 273 minus 273, and that will be negative 81 degree Celsius. And let's do a logical check here. What happened? The volume did decrease. Would the temperature decrease as well? The answer is yes. The temperature has to decrease as well. All good? All right. Another forms of Charles' law that you might see is saying that the pressure is directly related to the temperature as long as you have a constant number of moles and the volume is constant. So that's another way that we can say P1 over T1 equals P2 over T2. 2. Now, the pressure, if you increase the temperature, the collision of the particles will increase, and that will increase the pressure, right? And if you decrease the temperature, the particles will move slower, so that will be less collision, as therefore less pressure. Temperature, as again, must be in Kelvin. Next law we will cover is Avogadro's law, which studies the relationship between volume and the amount of gas. The more, think about charging a balloon with gas, with a pump, right? The more you charge, which means the more amount of gas, right? Moles of gas you put in, the larger the balloon is. So it's a direct relationship between volume and number of moles. If I increase number of moles, I will increase the volume. And therefore, it is written as V1 over N1 equals V2 over N2. As long as, this is very important for every gas law, as long as I keep the temperature and the pressure constant. And this is really important when we will learn about gas stoichiometry. So keep that in mind. Avogadro's law is always applicable at constant temperature and pressure. And why is that important? It means what happens to the moles happens to the volume. If I increase the volume, I will increase the moles, right? Because it is a direct relationship between volume and number of moles, which means it's equal volume times equals constant times N, which means V over N equals constant. To keep this ratio constant, if I increase the volume, I will increase the moles. And if I decrease the moles, I will decrease the volume, and so on. So equal volumes of any two gases contains equal amount of atoms, molecules, or moles, as long as I am under the same pressure and temperature. Okay? So 2 volumes of hydrogen reacts with 1 volume of oxygen to give me 2 volumes of water. Do you see what I'm doing here? Normally, I read the equations as 2 moles of hydrogen reacts with 1 mole of oxygen to give me 2 moles of water. But since what happens to the moles happens to the volume, as long as pressure and temperature are constant, I can now say what have also 2 volumes of hydrogen. So I can instead say 2 liters of hydrogen react with 1 liter of oxygen to give me 2 liters of water at constant pressure and temperature. I can use gallons, I can use liters, whatever it is. 2 conditions has to be there. First, all of them are gases because I cannot apply Avogadro's law on any other physical state. And constant pressure and temperature has to be mentioned as well. The ideal gas is molecules do not interact with each other. So if I'm going to talk about gases and I'm assuming ideal behavior, I am assuming that those gas particles are separated by large distances and they don't really interact with one another. They don't attract nor repel each other. The volume of gas is negligible compared to the container, which means that if I compress this gas, the volume that it will occupy in comparison to the container will be very, 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 very small. Ideal gases occur at low pressure and high temperature. This is important. How can I maximize the distances between particles? Because this is how they are ideal. I increase the temperature because then they are moving far away and fast from each other. And I also lower the pressure because if they are not under high pressure, it means I am not forcing them to get closer. I want them to stay further away from each other as possible. Now, the ideal gas equation is really looking at all these laws that we did talk about together and put them as volume is directly related to number of moles, that's Avogadro's, directly related to temperature, that is Charles', inversely related to pressure, that is Boyle's. Now, when I got rid of the equal, I have to put a constant, which is the R. So R here is what I call gas constant. And the way it's going to be written here so I can utilize it, it is PV. So I'm just rearranging this equation. PV equals nRT. This equation is what we call the ideal gas equation. Okay, so now let's calculate the gas constant. Our calculation of the gas constant has to come from one fact that we know about the gases under standard temperature and pressure, or what we call STP. So what is STP? It is when the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. That is what we call standard temperature and pressure. Here is a fact that we know at STP. 1 mole of a gas will occupy 22.414 liter, which what we call the standard molar volume. Standard because it's at standard temperature and pressure. Molar, it's because per 1 mole, right? And it is a volume. So this is something you need to know. If I have a mole of any gas at STP, the volume for it will always be 22.4 liter. You actually need to know this by heart, right? And you just need the 22.4. You don't need more digits than that. So 1 mole of a gas at STP will occupy 22.4 liter. Now, let's calculate R from that. At STP, what is pressure? It's 1 atmosphere. What is the volume? 22.4 liter. How many moles I am talking about? 1 mole. And what is the temperature? It's the standard temperature of 0 degrees Celsius, which equals to 273 Kelvin. If I put all these numbers down, I get the gas constant. Now you will be using the gas constant frequently, which is 0.08206 liter atmosphere for every mole Kelvin. Okay, it is 0.08206 liter atmosphere for mole Kelvin. Forget it. If you assume you will ever forget it, you can drive it again using the standard molar volume fact that you know about any gas. So pay attention though that in this specific R, we used the pressure to be in atmosphere, volume in liter, N is mole, and T in Kelvin. Now there is another R in which I'm gonna express the pressure in millimeter mercury, right? So what I'm gonna have right here, instead of 1 atmosphere, I am going to have 760 millimeter mercury. So if I have 760 millimeter mercury, what is the new value of R? And in this case here, 0.08206, and then I'm going to multiply this by 760 because everything else remained the same, and that will be, so this is another value for R, which is 62.4, and now the units for this one is, I'm going to put the units here, millimeter mercury, liter over mole Kelvin. So the question is, when am I going to use this one versus this one? It depends on the question you're solving. If you have the pressure in that question in atmosphere, then you're gonna choose the 0.08206. If the pressure in the question you're solving is in millimeter mercury, then you're gonna use the 62.4. Let's solve this question together. An aerosol spray deodorant can with a volume of 350 milliliter contains 3.2 grams of a propane gas as a propellant. What is the pressure in the can at 20 degrees Celsius? Okay, so here, this is not a before and after question. What you have here, you have information about the gas and one of them is missing. So I have volume, I have grams, which means I have moles, and I have temperature, and what I need is the pressure. So this is when I know it's not a before and after, therefore it's an ideal gas law. And the ideal gas law says PV equals nRT. And what I need now, I need to figure out the pressure. So P is going to equal nRT over V. I don't have N directly, but I can calculate it by converting grams into moles using the molar mass. So let's do that. So I have 3.2 grams, and then I'm going to say 1 mole of a propane will have the molar mass of 44.1 grams. Then I'm going to multiply by R, which is 0.0. 0.0821 for abbreviation times the temperature here. It's a 20 degrees Celsius, which is adding to 273, that is 293 Kelvin. Temperature has always to be in Kelvin in any gas law. And then the volume that I have is 350 milliliters sorry, I forgot to put the units, that's bad. So it's atmosphere liter for every mole Kelvin. So the liter is the volume, so I'm going to have to convert the volume into liter, which is 0.350 liter. Now let's do the math together. So that is 3.2 divided by 44.1 multiply 0.0821 times 293 divided by 0.350, and I'm going to have 2 sig fig because of 3.2, so the answer in this case will be 5.0 liter. And that's an application of how I use the ideal gas law. Now let's use standard molar volume in calculation. What volume in liter is occupied by 7.40 grams of ammonia at STP? Now, when I see STP, the first thing I do actually is to put this. At STP, here is what I know. 1 mole equals 22.4 liters, right? So what I need to do here, first I'm going to take 7.40 grams of ammonia. I'm going to convert it into moles, right? I'm going to say 1 mole of ammonia. And now ammonia, 14 for nitrogen, and 3, that's 17.04 grams of ammonia. Times, now I will use this as a conversion factor, right? For any gas at STP, which is what the situation is, I can say there are 22.4 liter for every 1 mole of ammonia. So there is 22.4 liters of ammonia for every 1 mole of ammonia as long as I am at STP. So 7.4 divided by 17.04 multiplied by 22.4. The answer here with a 3 sig fig will be 9.73 liter of ammonia. All right. A combined gas law, it's a modification of the ideal gas law, right? So what we are going to do here, we use problems that involve changes in not only one thing, like not only one parameter, but it can be multiple parameters. Now R is a constant, and R equals P1 V1 over N1 T1, which will, if I change, let's say I change the pressure and the temperature, what will happen to the volume under constant moles or something like that. And before, since R is a constant, is not going to change, then that will be P2 V2 over N2 T2. Okay, so this is the combined gas law. It's really, I combine all the laws together, and P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, if the moles are the same, and what does that mean to you in a question? How do you know that? It means that they are talking about one sample, and there is no mentioning of that they lost any of the sample or they added anything to the sample. That indicates that the amount or the number of moles are constant. In this case, I only use P1 V1 over T1 equals P2 V2 over T2. Why? Because if the moles are constant, simply they're going to cancel out from the equations anyways, right? That's just mathematically correct. Okay, so let's look at this together. A gas initially at 4 liter, 1.2 atmosphere, and 66 degrees Celsius. You see here, I am giving 3 parameters of before. It undergoes a change so that the final volume and temperature are 1.7 liter and 42 degrees Celsius. They changed the volume and the temperature. What is the final pressure? What is the final pressure of the gas? Assume number of moles remains constant. There is no mentioning of adding or losing. So it means that I'm gonna choose to use this one here. And what I am solving for is P2. Right? So if I am writing these equations together, I'm going to write it up here, in which I'm going to like have the cross multiplication. This says like P1 V1 T2 equals to P2 V2 T1. And what I am solving for is P2. So P2 here equals to P1 V1 T2 divided by V2 T1. Now this is where you start to appreciate that columns that I talked about before, because now you can see that you have condition 1 and condition 2, right? Before and after. So the before, you have V1 at 4.0 liter. You also have P1 at 1.2 atmosphere. Then you have 66 degrees Celsius, immediately add 273 to that. So this is 933 Kelvin. Okay? At 2, what do you have? You have V2 at 1.7 liter. And then you have T2 at 42 degrees Celsius, immediately at 273. So this is 513 Kelvin. Okay? Now put all these numbers together. So I'm going to use this here. And I'm going to say, okay, well, P2 equals 2. At the top here, I have P1. I labeled P1 as 1.2 atmosphere. I labeled V1 was labeled as 4.0 liter. Multiply. And T2 is 315 Kelvin. V2 was labeled as 1.7 liter, multiplied by T1, which is 339 Kelvin. Okay, this is why this becomes really helpful here. So now let's put all this together in our calculator. So what we have is 1.2 times 4.0 times 315 divided by 1.7 divided by 339. The answer is 2.6 atmosphere. Okay, so this is how we utilize the combined gas law. It means we are changing more than one variable at the time, and you either have the moles changing as well, and in which case you're going to choose the one that include the n, or if the n is constant, then it's P1 V1 over T1 equals to P2 V2 over T2. That is the end of this lecture right now, and I will see you in the next one. Thank you.